Hi, welcome friends. So in this example, what we are going to do is that we are going to discuss about a system in which the moment of inertia will be a function of a generalized coordinate system phi. So let's just, start with the problem statement. So this system represents a slider crank mechanism which is pivoted at this point O. Now in this system there are total 5 number of mass. So first one is this one is the ml, second one is this rectangular block ms, third one is this block with mass me and length e, and fourth one is your this block which is connecting o dash to this another pivot point that is located at this rectangular section. Now the length of this block is b. Now first what we need to find is in this case is that if we look at this image, suppose that if I am going to give a rotation about this pivot point of any angle phi, so what will happen is that this rectangular block will move to a new location. So when it moves to a new location, the distance between the point O and the CG of this mass block will change. Like for example, after the translation of this block, the new CG location will be around this point. So automatically, as we are changing the value of phi, the distance between O and the CG of this block will change. Now, if we go back to our basic definition of polar moment of inertia, using which we are computing the polar moment of inertia about any reference, another reference point, uh, then the definition was like this: J0 is equal to Jg plus ma square, where a represents the distance between the reference point and the CG of that component. Now in this case, this a will continuously change as a function of phi. So for this case, what we can say that just by looking at only one system, we can say that the total polar moment of inertia of this system is not going to be a constant value. It will change or update with the change in this coordinate system phi, or with the change in phi, we can say. Now if in order to derive this equation, like suppose that if we want to develop a relation between r a and b, or r e and a, or any other system. So looking at this image, what we can see is that if we look at this o, this cg of this block, and this o dash, it represents a triangle. Now if we go back to our cosine law, then in that case, if we want to write as derive the formula for r as a function of phi, then it will become r square is equal to a square plus b square minus 2ab cos phi. So this is our first equation. Similarly, if we are going to derive a relationship between the CG of this block CG of this block and also CG of this block. So what will happen is that in that case, our RB square will be equal to b by 2 square plus a square minus ab cos phi. This will be our second equation. Similarly, re square will become e by 2 square plus a square minus ab cos. Now here, when we are going to take the angle between a and e by 2, that angle will be pi minus phi. So here we have to use pi minus phi. So this will be our third equation. Now this distance mainly represents the component level distance between of a for each component. Now when we are going to derive this polar moment of inertia for the whole system, then that will be a summation of your j of ms plus j of ml plus j of mb plus j of me. So each individual mass system will contribute to the overall polar moment of inertia. Now, if we look at this first, this block. So this block is simply rectangular block with a CG location at L by 2, and that CG location is not going to get affected by change in phi. So we can first write JML is equal to ML square by 12 plus M into L by 2 square, and that will give us ML square by 3. Similarly, if we are going to write the equation of polar moment of inertia at point O due to the mass ms, so then that will give us J of ms is simply equal to ms into r square. And if we are going to write for mb, so it will be mb b square by 12 plus rb square, and J for me will become me e square by 12 plus re square. So looking at all the equations, what we can say is that Jms is a function of phi, Jmb is a function of phi, Jme is a function of phi. So as the phi value changes, it will directly going to affect your polar moment of inertia value, and which will also affect the equations that the governing equations that you are going to solve. So for this video, mainly the motive for this video was to demonstrate that the polar moment of inertia is not a constant value. With respect to the system or with respect to any coordinate system, it keeps on updating. So it also makes your equation non-linear. So we will discuss in detail about this type of behavior and what are the behavior, what are the effects that varying inertial property is going to make in our main governing equation. So we will discuss about that in our later part of this video series. So for now, this is all about this video series. This video. Thank you. And if you like the video, please like the video and also subscribe the channel. And in that case, if you think that we can further improve or any point, please write that in the comment window. We will try to improvise on that. Thank you.